Thank you very much. So good afternoon, everyone. My name is Capanema. I'm a PhD student from PUC, Rio de Janeiro. And today I'm going to talk to you a bit about my research in electromagnetic cascades and their role for high energy neutrino astrophysics. Is it this one?
Yeah, it should be. That's
Maybe
not working. Let me try again. Yeah.
Okay. So as somebody working in high energy multimessenger astrophysics, I'm interested in three main messengers. Ultra high energy cosmic rays. Of course, we have talked a lot about them already, and I'm not going to talk too much about it. But these have been observed up to energies of 10 to 20 electron volts or such. And they are important for probing the acceleration mechanisms and production of particles and their sources. I'm also interested in high energy gamma rays, which if you look at the sky above TeV energies or so, actually become quite rare. And this is because the energetic enough gamma rays can actually get absorbed by photon backgrounds that permeate our universe, such as the cosmic microwave background or the extragalactic background light. Walter has already mentioned, talked a lot about this. And although this might seem like the end of the story and the high energy gamma ray is lost, it can actually get regenerated at a slightly lower energy than the original gamma ray once these electrons or positrons inverse Compton scatter off of new background photons. And this chain reaction of pair production inverse Compton scattering happening over cosmological distances is what is known as an electromagnetic cascade. And this leads to production of a sub-TeV gamma ray flux at the Earth. Finally, of course, I'm interested in neutrinos, and in particular in the high energy astrophysical neutrinos being detected by IceCube. So let's quickly recap what IceCube is seeing. IceCube is observing a diffuse flux of neutrinos from extragalactic origin, whose sources are, as you all know, we don't know. And depending on their different background rejection methods, IceCube classifies its events into different data sets. So here I show you three data sets, and they actually fit their astrophysical neutrino flux with a power law with two pre-parameters, an overall normalization phi astro and a spectral index gamma astro. There's actually a third important characteristic of these fits, which is a low energy threshold, below which the atmospheric backgrounds start to dominate over the astrophysical signal, and IceCube can't really tell what's going on below this threshold energy. And this is crucial because, as we have seen, based on the production mechanism of these neutrinos, we actually expect that there should be some sort of a spectral break happening below this low energy threshold. And in fact, if you want to be as conservative as possible as to what is the possible emission spectrum of the IceCube neutrino sources, we can assume that they are some sort of broken power law with a break energy happening below the threshold energy that IceCube is seeing, because IceCube is not seeing any break in the spectrum so far with any significance. So this is the most conservative assumption you can make for the emission spectrum of these neutrinos. Of course, these neutrinos are not produced by themselves. We have seen this a lot. They are necessarily accompanied by a comparable flux of gamma rays. And actually, once you work out the energetics of these processes, you end up with a really nice relation between the emission spectrum of neutrinos and the emission spectrum of gamma rays at these sources. And this is a very conservative back of the envelope calculation, you could say, not accounting for any extra gamma ray emissions coming from processes different from the P gamma or PP. And also, we're not assuming that they get absorbed inside of their sources. And actually, this is going to be, I guess, the main point of this part of my talk, understanding if these sources have to be opaque or not. Where are these gamma rays getting detected? Of course, they're being produced at TeV to PeV energies, the energies around where we're detecting the IceCube neutrinos, and they cascade down to sub-TeV energies where we have observations of the extragalactic gamma ray background by the Fermi-Lat telescope. And here I show you the data, the EGP data by Fermi. And we have already understood the three main well-established contributions to the EGB. These are contributions from blazars, radio galaxies, and star-forming galaxies, which are called the conventional EGB contributions. And together, they already account for nearly 100% of the EGB data, leaving very little room for any extra contributions to the EGB data. But we know that whatever the sources of the IceCube neutrinos are, if they are also emitting gamma rays, this gamma rays should cascade down and become an extra contribution to the EGB, which I'm going to call the cascaded contributions. So the game we can play is basically add the cascaded contribution based on what we're observing at the IceCube flux, add these to the conventional contributions, and see if we can fit the EGB data or not. And this would, in principle, establish a tension or not a tension between the IceCube data and Fermi data. So let's take a look at how this is done in practice. We start by assuming a given set of parameters, a normalization, an emission spectrum, sorry, power law index, and a break energy, and such that they interpret the IceCube data. And then we can calculate the corresponding gamma ray emission spectra at the sources. And then we need to propagate these particles all the way to the Earth. Neutrino propagation is fairly straightforward because they don't interact. So you just need to take into account cosmological redshift effects. And also you need to introduce this F over here, which encodes the information regarding the distribution of your sources in the universe. So the redshift distribution of your sources. And we can easily evaluate this. Gamma ray propagation, on the other hand, is much more complicated because of these electromagnetic cascades. And in fact, for the precision that we require for this work, we require numerical simulations. And for that, we have used the code gamma cascade, publicly available code gamma cascade. And here on the left, you can take a look at two examples for two different assumptions regarding the redshift distribution of sources. So in green, we have results assuming that the IceCube neutrino sources follow the star formation rate in the universe. And in red, assuming they follow the BL-lac distribution in the universe. The dashed lines are the neutrino fluxes, assuming that we choose initial parameters according to the best fit values of the Cascades dataset at IceCube. And the solid lines are their corresponding cascaded gamma ray fluxes, which when added to the conventional contributions, you can actually see that they don't provide a really good fit to the EGB data. There's actually an undershoot at lower energies and an overshoot at higher energies, depending on which evolution you're assuming. So the question remains, is there any choice of parameters that can interpret both the IceCube data and the Fermi data simultaneously? So after scanning the entire parameter space and performing chi-square fits to the EGB, we found that the answer is probably not. We also tested several different redshift evolutions, and here I show you results for two of them. So if you take a look, for example, at the SFR, our black lines, these contours, anything above that is excluded by Fermi or in tension with Fermi at 2 sigma level. Of course, how significant is this tension really depends on if you want to be very optimistic or very pessimistic regarding the true value of the spectral index and the overall normalization that IceCube is seeing. So the takeaway message that I want to give you here is that most likely for any set of parameters conceivable that can fit the IceCube data, there is at least some level of tension, which implies that these IceCube neutrino sources have to be somewhat gamma ray opaque. They need to reprocess these gamma rays to lower energies or block their escape quite significantly in order to avoid any tensions. So I'd like to move on with the remaining time that I have and talk about some more recent things that I've been working on regarding the cascade, in particular some phenomena that may arise at ultra high energies. So the question that I actually want to answer is, can we produce neutrinos in cascades? Which might seem like an odd question at first, but yeah, I mean, you just have a gamma ray propagating, how are you going to produce a neutrino? But it's an idea that has been growing in popularity lately, which is considering this interaction here, muon pair production. So when a gamma ray encounters a background photon, instead of producing an electron-positron pair, you'd produce a muon pair, and then the muon would, of course, decay into neutrinos. Now, how do we assess the feasibility of this interaction actually taking place? First of all, it has a much higher threshold, so it kicks in at much higher energies. So you need cascades starting at ultra high energies. And if you compare their mean free paths, very naively, you would expect that pair production always dominates over muon pair production. And so you wouldn't expect any neutrinos to be produced, at least in any measurable amounts. But this is a very naive expectation. In fact, after electron pair producing, we have seen that inverse Compton scattering regenerates the gamma ray. And so you have a new opportunity to muon pair produce, right? So you shouldn't be comparing their mean free paths. You should actually be comparing the energy loss length of electron pair production with the mean free path of muon pair production. And then you start seeing that above 10 to 19, 10 to 20 electron volts, you actually have the possibility of muon pair production taking place. Of course, at such high energies, there's a new interaction that kicks in, which is double pair production. So that would be producing two pairs of electrons and positrons. This dominates at in the high energy tail. So there's actually a very narrow window around 10 to 20 electron volts where you can actually produce such muons. So far, we've been talking everything locally. So at redshift 0, and at redshift 0, in fact, you have the presence of the cosmic radio background, which unfortunately just dominates the interactions at ultra high energies, and we cannot produce these muons. However, if we're talking about cascades happening at high redshifts, there's no cosmic radio background anymore. And then you can actually, in principle, have such interactions and such neutrinos being produced. Okay, this is just a proof of principle. Does this actually happen? So we ran some Monte Carlo simulations. And you can actually see that at 10 to 20 electron volts, a considerable fraction, so this is the fraction of energy of the original gamma ray that is converted into neutrinos. A considerable fraction of the energy starts to be converted into neutrinos. So you actually have quite a few muon pair productions occurring along the cascade of an ultra high energy gamma ray. And if you want to know how the flux looks like at the Earth, these are represented by these blue curves, and they can actually be distinguished from they dominate over the conventional pion decay flux that one would expect from an astrophysical source by 1 order of magnitude or 2 orders of magnitude, depending on how optimistic you want to be, at slightly lower energies far from the one last thing that I would like to mention is that this process is responsible for transferring some of the gamma ray energy budgets emitted at these sources into neutrinos. So actually, if you have a high redshift source of ultra high energy particles emitting neutrinos and gamma rays, this process is responsible for making the source gamma ray darker and neutrino brighter. So these energy budgets can be redistributed and more energy is dedicated into neutrinos. And this is all I wanted to say. So thank you very much. Sorry, this thing here? Oh, sorry, because this is your target photons are CMB photons, for example, and they're going in random directions, right? So your cross section for pair production really depends on the direction that the gamma rays encounter each other. So this is actually an angle averaging over the cross section, and you need this factor actually to correct for the relativistic angular aberration formula. Basically, it's a relativistic factor to correct for the angle averaging over these cross sections. And of course, to estimate mean free paths, you have to take the angular average cross section because you don't really know what angles it's gonna find the target photon, basically. Yeah.
So I have a very naive question.
Yeah.
But you're considering pair production from gamma scattering, right?
Mm-hmm.
Can you actually produce neutrino pair by loop diagrams, for example, in this case, and produce lower energy neutrinos?
You can. They will be very suppressed, though. I mean.
Yeah. That's my question. How would they compare to given count in this case?
I haven't actually seen in the literature this being done, but I would assume that it will be much more suppressed. They would be not comparable. These loop effects. There have been some like if you go to extremely high energies, you can start thinking about producing pion pairs or something like that, or yeah, heavier particles basically. But loop effects, I don't think so.
Okay. Questions?
Let's say Antonio again. The next speaker. It's and do you have a PDF? No. Let's be.